This is Doug Lowen, Associate Professor of Public Policy at UNC Chapel Hill. This is the fourth part of my video tutorial on bivariate statistical testing. Now we're to the fun part where we can actually look at some results. As you can see, it takes a long time to get the data together and get it recoded and double check it to make sure everything's okay. As the saying goes, garbage in, garbage out. You got to make sure you do those preparation steps carefully so that you can get interpretable results. So we're now going to just perform some statistical tests. The first one is a t-test, and that's appropriate if you have a continuous dependent variable, which in this case is a reading score, and a binary independent variable or predictor variable. In this case, this is a binary variable called pupil-teacher ratio, and it has two categories, high and low. Okay, so our hypothesis would be that our hypothesis is that reading scores would be higher if pupil-teacher ratio is lower. So we expect that the mean reading score would be higher in this group where the variable pupil-teacher ratio is low than it would be when pupil-teacher ratio is high. Okay, so let's just run the summary statistics without any statistical testing and see if our hypothesis of our hunch is correct. Okay, and that's what we find. We find that the reading test score is higher in the low pupil-teacher ratio group than it is in the high pupil-teacher ratio group. So it's 222 in the low group and 217 in the high group. Okay, so there's not a lot of states, so it could be that the statistical test here would test the difference between these two groups, 222 minus 217, and we might have enough power to detect an effect, or we might not. And power, what I mean by power is that we don't, if we have large n, we have more power. And if we have low standard deviation, more precision in our estimates, then we also have more power. Okay, so let's go back, run our t-test, and if you need more information about this test, then you should just type help t-test in Stata to get more information. But we put the dependent variable after t-test, we have a comma, and then our x variable goes in this by statement here. We're assuming unequal variances, which makes sense because it looks like there is different standard deviations in these two groups. So let's highlight that, click do, and we see that just as our summary statistics suggested, this is the mean for the group that has low pupil-teacher ratios. That's shown here. And then for the high pupil-teacher ratios, that's shown here. Okay, so the means are there. The mean difference is about 5. Okay, and the t statistic is 2.85, which is statistically significant at the 0.05 level. For the two-tailed test, and obviously for the one-tailed test as well. So the p-value is very low, which tells us that we have a very low probability of making a type 1 error, which is falsely rejecting a true null hypothesis. So the degrees of freedom, this is the Satterthwaite's degrees of freedom. That's a pretty complicated calculation. It's beyond the scope of what we're going to do in this tutorial, but it's about 47. We have 51 states, so that's our approximate degrees of freedom. So let's go on to the proportion test. So we can say that that these two means, the mean difference here is statistically different from 0. That's the null hypothesis. So we have support for our research hypothesis that the mean test score in states that have low pupil-teacher ratios is higher than states that have high pupil-teacher ratios, and the difference is about 5 points on the NAEP scale. Okay, I'll move on to the proportion test in the next tutorial.